In this video we will introduce a new function combining y and s functions to get the advantages from both. From the shape of the curve, it will be conveniently called v function. Here is the basic formula of v function. There are two constants and one variable to draw the plot. Just like y and s functions described in previous videos, d represents the difference in position between the complex input of zeta function and the critical line. This is the variable being plotted along the horizontal axis. A constant c determines the magnitude of imaginary part in the input of zeta function. The new constant b determines the multiplier of variable d for the numerator of v function. Let's see how this new constant b affects the shape of v function. We can see the minimum point better when zoomed in. In this plot, b is 10. This is the plot where b equals e, the Euler's number. The real curve crosses the critical line at exactly 1. This is the plot where b equals 1 over e. The real curve crosses the critical line at exactly -1, and it is vertically inverted. This is the plot where b equals 0.1. These examples show that real part of v function intersects with the critical line at log of b. When b equals 1, log of b is 0. The numerator becomes equal to the denominator. The plot of v function overlaps with the real axis. From these observations, we can conclude that real part of v function is always positive when log of b is positive. It is always negative when log of b is negative. It is always 0 when log of b is 0. Let's see if this crossing point is affected by the value of imaginary part c. Note that when b equals 1, the numerator is exactly the same as denominator, regardless the value of c. Thus the v function overlaps with the real axis. Now the value of b equals e. The real curve crosses the critical line at 1. The higher value of c increases the slope. Now c equals 14.1347, which is close to the smallest non-trivial zero of zeta function. The real curve crosses the critical line at exactly 1, and it still has a smooth shape. Now c equals 2 pi. The real curve crosses the critical line at exactly 1, and it is almost a flat line. So, let's zoom it out to see the bigger picture. Now c equals 5. The real curve still crosses the critical line at exactly 1, although the shape is getting more complicated. Now c equals pi. It seems that the value of c has no effect on the intersecting point between real part of v function and the critical line. Now c equals 1. The real curve still crosses the critical line at exactly 1. But the shape looks incomplete. So, let's zoom it out to see the bigger picture. Now c equals 0. We get some periodic spikes. Even now the real curve still crosses the critical line at exactly 1. Now c equals -1. The real curve is the same as when c was +1. Only the imaginary curve is inverted vertically. When c has a low magnitude, the shape of v function is complicated. Let's see how it behaves at higher magnitude, starting with 1000. Just like s function, the real plot of v function has more regular shape with higher magnitude of c. In this plot, c equals 1 million. Now, it's the time to show how the behaviors of v function are related to anomalous zero of zeta function. For the sake of the argument, let's assume that there exists anomalous zeros of zeta function. Here are the implications. D sub a doesn't equal 0. C sub a is larger than 1 million. Zeta of a half plus d sub a plus c sub a I equals 0. Zeta of a half minus d sub a plus c sub a I equals 0. denominator of v function is 0, and v function blows up, except if the numerator is also 0. For any finite real value of b, zeta of a half plus p d sub a plus c sub ai equals zeta of a half minus p d sub a plus c sub ai. It means that zeta function at this particular value of imaginary part must have a mirror symmetry about the critical line. Since b can be any finite real value, then b times d sub a can also be any finite value. Thus the formula can be simplified to zeta of a half plus d plus c sub ai equals zeta of a half minus d plus c sub ai, with d can be any finite real value. But if b is chosen large enough, d can exceed a half. It makes the input of zeta function outside of the critical strip, which means the zeta function cannot be 0. Thus to make the numerator of v function 0, zeta function for positive d must be exactly the same as zeta function for negative d, providing that the imaginary part is the same. But it then requires the zeta function of a complex number with real part higher than 1 to be equal to zeta function of a complex number with real part lower than 0. All of these requirements contradict the known behavior of zeta function as shown here. The left pictures show the plot of zeta function with a constant imaginary part, while the right pictures show the logarithm of the same zeta function. In any case, those plots can never be symmetrical about the critical line. This contradiction can only be resolved when non-trivial zeros of zeta function are all located on the critical line, which makes d equals 0. Thus, Riemann's hypothesis must be true.